Hi everyone, for this lesson we'll be covering dynamics. So the study of dynamics is all about reaction rates, how fast reactions occur and factors that affect that. So in order to establish this, we need to measure the reaction rate. So we consider the following reaction where we have hydrogen gas, oxygen gas going to water. The stoichiometry is going to affect the rate at which these substances appear and disappear. So the disappearance of H2 occurs twice as fast as the disappearance of O2, and that's because of the stoichiometry here. So if we look at the number here, we've got 2 compared to 1, and so for every water molecule that's going to be formed from these, I need twice as much H2 as I do O2, because the ratio of hydrogen to oxygen is 2 to 1. And so that means that the H2 is going to be used up twice as quick as the O2. So I can write this as delta being the change in. So the change in the H2 gas concentration, so the square brackets mean concentration. The change in the H2 concentration relative to time, the change in time, is going to be twice as fast as the change in the O2 concentration with respect to the change in time. Or rearranged, this would be a half times the change in the H2 concentration times the divided by the change in time compared to the change in the O2 compared to time. So all I did was just took the 2 from there to make a half. So multiply both sides by a half. Okay, so this is important because just here we can see that one way of comparing one thing to another would be to have 1 divided by the stoichiometry here. So this is 1 divided by 2 because the 2 there. So this is really just demonstrating why this would be the case if I'm trying to compare apples to oranges, more or less. If I'm trying to compare one species to another with different stoichiometries, I can look at it by this method here. So the general form, if you have a reaction A lots of A plus B lots of B goes to C lots of C and D lots of D, the rate overall would be given as firstly minus 1 over A concentration of A changing and concentration time changing. Firstly, the minus means that it is decreasing. Because A is being used up, the change has to be a negative because the final is always going to be less than the initial, and so that will give you a negative. So we put another negative at the front to balance that out, because the rate of reaction always has to be positive. So that's why whenever you use a reactants, you always put the minus signs out the front. The 1 over A, again, as we just saw before, is because I divide 1 by the stoichiometry so that I can compare things. So overall, the rate is really looking at what it would be for one molecule to go across. Okay, and so in order to compare different things, we divide by those stoichiometries. With the products, there is no negative in the front because the products are being formed. So the final, so in the changes in the final minus the initial, there's always going to be a positive value. So you just maintain the positive out the front. So let's consider the following reaction. So the rate of appearance of the NO2 in this reaction is 5.2 moles per litre per second. What is the rate of the reaction? So looking at what we've got here, the rate should be equal to 1/2 the change in the NO2 concentration divided by the change in time. And so that's exactly what we have here. The rate equals 1/2 change in NO2 concentration, change in time. So it's 1/2 times the 5.2 moles per litre per second, and so we get 2.6 moles per litre per second. So another question, we have methane gas plus O2 gas going to CO2 plus 2 lots of water. The rate of water formation is 3.4 mole per litre per second. What is the rate of CH4 disappearance? Okay, so again, we need to bring it back to some commonality, which is the rate expression. So rate equals 1/2 concentration of H2O over change in time, because it's a product, equals minus the change in CH4 over change in time, minus because this is CH4's on the reactant side. And there's just a 1 here, so it's 1 divided by 1. So there's no need to worry about that. Okay, so the rate would also be equal to minus 1/2 the change in the O2 versus time, and also equal to positive the change in the CO2 over time. But because these species here aren't part of the question, I don't need to worry about including them here. Okay, so now the change in the CH4 over time, which this part here is the rate of the CH4 over time, is going to equal minus 1/2 of 3.4 mole per litre per second, because this has just been rearranged here. Okay, not rearranged. It's been substituted in what the water value is, 3.4. Okay, so I hope that makes sense. So the overall rate here is going to be minus 1.7. I should put the units there, moles per litre per second, and so the rate of disappearance is going to be a positive of that value. It's just a semantics really, but when you say disappearance, it's already understood that you've got a negative increase in concentration, if that makes sense, and so disappearance you can just have as a positive value. Okay, so again, just semantics. So the rate law. So the measure of the rate is really like a car speedometer. If you drive along and you're doing 60 miles an hour, that speedometer is telling you how fast that car is traveling. Now, depending on where you are driving, you will have different speed zones. So the law of the land tells you how fast you should drive in a certain part of town, and the rate law is similar in that it governs the reaction rates and how concentration affects those reaction rates. So it doesn't do away with what we have before. So with our example here, we have carbon monoxide and NO2, and this should be really written like this, going to carbon dioxide and nitrogen oxide. The rate law is K times NO2 squared. Okay, so now when we have rate laws, they're not always what you would expect of the stoichiometry. That's why I wrote this sentence. Reaction stoichiometry is not always a reliable predictor of reaction rate. Okay, so you would probably expect you'd have a concentration of carbon monoxide in there somewhere, but that's not necessarily the case. Okay, so just be careful with that. Reaction rate laws are not always able to be viewed and determined via the stoichiometry. Sometimes it works out that way, but often it doesn't, and I won't go into the full reasons for that, but basically it's because this reaction would have several steps in it. Okay, so the reaction is zero order in carbon monoxide, meaning that carbon monoxide is not involved. Okay, and second order in NO2. Second order because the power here, the indice, is a 2. This can also be expressed as rate equals K, a different K than this one probably, and so K times the partial pressure of NO2 squared. Okay, so you can look at it in terms of pressure as opposed to concentration as well, partial pressure I should say. So if we have another look at a law like this one, we have rate equals K times the concentration of A squared times the concentration of B. This will be second order in A because the indice is 2. First order in B because there's really a 1 there. We don't write it in, but there's really a 1 there. And third order overall. Third order because you add the indices for the different components. And so we have 2 plus 1 is 3. So this one here, the rate's K times concentration of A, concentration of B, concentration of C squared. It's first order in A and B, second order in C, and fourth order overall. Okay? So U is not very clear there. Okay. So, let's do another example. The rate constant for a reaction is 1.9 by 10 to the 2 litres per mole per second. reaction is second order with respect to A. Calculate the rate of reaction when the concentration of A equals 0.72 moles per litre. Okay, so given our information, our K, which is our rate constant, we can put that in here. And we know it's second order with respect to A, so it's concentration of A squared. So we put in our concentration of A, 0.72, and have it squared, and we calculate that and get 98 moles per litre per second. So that is the rate that the reaction will have when that A concentration is 0.72. As that A concentration varies, as it will over time, this will also vary. In this case, it will decrease. So the units of rate are always mole per litre per second. They can vary depending on the context you're using, but for our purposes, they'll always be moles per litre per second when you're dealing with concentration, at least. If you're dealing with partial pressure, then you'll have different units, which would be atmospheres per second. Okay, so the units of K, the rate constant, do vary. So because we need to maintain this rate as moles per litre per second, then these units here, this at the moment the unit for A is moles per litre, and so the squared means it's going to be moles squared per litre squared, and so K will have to change in order to be able to multiply the units from the K and the concentration term to still end up with the units for the rate being mole per litre per second. So if we have a look at it, I've constructed a table for you. If the order of reaction is 0, then the units of K are just moles per litre per second. If the order of reaction is 1, then the units of K are just per second. 2, litres per mole per second. 3, litres squared per mole squared per second. A way to remember this is that you basically get moles per litre, but you invert it, so it becomes litres per mole, and then you have that to the power of n minus 1, where n is the order of reaction. The s is always to the power of minus 1. So you notice through here, always maintain s to the minus 1. Okay, so let's say you had a fifth order reaction. Then it would be litres to the 4, moles to the minus 4, and then still per second to the minus 1. Okay, so if you notice here, this is 3, these numbers here are 2. Okay, if it's 2 here, these numbers are 1. Okay, so I hope that makes sense. Here, it's a 0, so it's going to be minus 1. So it would be litres to the minus 1, which happens there, and moles to the plus 1, which is there. Okay, so this equation here will help you determine that. You can always check, if a question comes up like this, you can always check to make sure that your units, when they multiply through, are consistent. And I would encourage you to do that. So let's have a look at some zero order reactions. So the rate law for a zero order reaction is the change in the concentration of A with respect to time is just equal to some constant K. So that means that as, and again I've got the minus here because the A is the reactant, and so the minus is just saying that as the change in the A proceeds, which is going to be a minus value, then I'm going to get a positive. Because remember, the rate we always want to be a positive value. So you can just look at this first term as rate. I could easily just write rate instead of this term here. So my rate would equal K. If I integrate that, which I'm not going to go into how to do that, but if you integrate it, you will get the concentration of A equals the concentration of A naught. A naught is our initial value. Anytime you see a naught there, it means that we're referring to an initial condition. Okay, so our concentration of A is equal to our concentration of A naught minus KT. So a plot that we have linear, if you remember y equals mx plus b, if I plot concentration of A versus T, then I'm going to have a slope of negative K. This would be like negative K would be my M, T would be my X, and Y would be my concentration of A. Okay, so Y equals mx plus b. So I'll have a slope of negative K, and the intercept, which would be our B, is the concentration of A naught. You should Google these. Wikipedia's got a great summary of these, and and it's worth having a look at, so you remember. So here, the rate equals K times the concentration of A. First order because the A term appears, it's really got a 1 there. In the previous question, this would really be A to the power of 0. You could put an A to the power of 0 here, okay? But the concentration of A to the power of 0 is just 1. Any number to the power of 0 is 1, so it doesn't appear there. Integrate this and you'll get concentration of A equals concentration of A naught, e to the minus KT. When you when you take the natural logs of this, you'll have natural log of A equals minus KT, because this e to the minus KT, when you take the natural log, would become minus KT. And then this part here becomes natural log of A naught. So a plot of natural log of A versus T will still give you a slope of minus K. But now you'll have an intercept of natural log of A naught. Okay, and again you'll have a plot that looks something like that. Second order reactions. So the rate is going to be K times A squared. Integrated rate law is 1 over A equals 1 over A naught plus KT. So now we have a plot of 1 over A versus T. We have a slope of K. Okay, so now it's positive K. So it's going to go up instead of down like the other ones. And our intercept would be 1 over A naught. These are going to be hard to remember, but again, it paid to look in the textbook or even somewhere else online to see a comparison of all these orders of reactions. Now we come to half-life. So half-life is really the time that's required for half of a substance to decompose or react, or if you've got nuclear reactions, for one isotope to turn into some other element. So 0 order, we have T to the half, which is just the way we write the time for a half-life. For a 0 order, it's a concentration of A naught over 2 times the rate constant. That's a K there. So for the first order, it's a natural log of 2 divided by K. The second order, we have 1 over K times concentration of A naught. Okay, so just using those equations, we have a second order reaction has a rate constant of K equals 7.2 by 10 to the 2 liters per mole per second. If the initial concentration of the reactant is 0.0172 mole per liter, calculate the half-life. So you just put it into your equation for the second order, which is here. You put that in, and you just have 1 divided by your rate constant and your concentration here, and you get this time, 0.081 seconds. Perhaps try and repeat this calculation in your calculator and make sure you achieve the same answer. So another question, for a first order reaction, the half-life is 2.72. By the way, just so I can emphasize something, if you notice from this half-life sheet with these equations, it's only the first order equation that is independent of concentration. So first order reactions have half-lives that it doesn't matter how much of the substance you have at the time. The 0 and second order reactions are going to depend on how much of the material you have. Okay, so back to this question. For a first order reaction, the half-life is 2.72 seconds. If we initially have 200 grams of material, how long will it take till 50 grams of material remains? So after one half-life, so half-life means the time taken till half the substance changes. So after one half-life, the 200 grams will be reduced to 100 grams. If you have another half-life, that 100 grams will then be reduced to 50. So we can see that we really have 2 half-lives that are happening. And so I'd get the 2 multiplied by the half-life, and I get 5.44 seconds. So 5.4 seconds are 2 sig figs. So that's the time required to get to 50 grams when starting from 200. So activation energy and Arrhenius considerations. Activation energy is the energy required to allow a reaction to proceed. So if you remember from previous discussions, we looked at graphs like this. We have reactants and products, and at delta H is the change in the enthalpy there. between the products and the reactants. Now, the activation energy is the hump. That's the amount of energy required to push a reaction into its transition state. And so you need that minimum amount of energy if a reaction is going to proceed. It was discovered some time ago that the rates of equations, in particular the rate constant, is dependent on temperature. Okay, so here we have A. Now this A is completely different than what we've been discussing before as A as a representation for the species. This A is the pre-exponential factor or frequency factor. Okay, so and I'll most often refer to it, and it's probably most commonly referred to as a pre-exponential factor, but it does have a couple of other names. So A times E, that's the exponential function, to the power of minus EA on RT, where EA is the activation energy. And so if you take the natural logs of these, you'll get natural log of K equals minus EA on RT plus natural log of A. Now the R you've got to use is 8.314 joules per Kelvin per mole. Do not use the other one that we use in the gas constant as a gas constant, 0.08206 litres atmospheres per mole per Kelvin. Don't use that one. So if we plot the natural log of K versus 1 on T, you can see from here natural log of K versus 1 on T, the 1 on T here, that means that this minus EA on R is like our gradient, our slope, and so gives a slope of minus EA on R and an intercept of natural log of A. Okay, so that's a very, very common plot. In order to calculate activation energy, you'll plot the natural log of the rate constant versus 1 on T, and that'll give you the value for that activation barrier. So the activation energy for a particular reaction is 100 kilojoules per mole. By what factor will the rate constant increase when the temperature is increased from 30 degrees Celsius to 40 degrees Celsius? Okay, so here we've got a reasonably complicated equation. Now on your assignments you should have a data sheet down the bottom that has this equation for you. It's really just a matter of I won't derive the whole thing, but really it's just a matter of dividing one, K equals AE to the minus EA on RT divided by another one, K2 equals AE to the minus EA2 on RT2. Okay, dividing those two, and then if you've got the same activation energy, then you can just have one of those, and you can look at the comparison of the rates constants versus our temperatures here. So that might be worth you trying to derive to get a better understanding of how this equation works, but I won't go into too much detail. So all I really have to do is to plug in the values. Now, if you notice, I've got the K2 here on top and the K1 on the bottom. That means that the T2 must come second here and the T1 comes first. So be careful when you put in these values. If at the end of this you actually get a negative number, then it's okay. You can just take the reciprocal right at the end here. So if this came out as a negative at this point here, then you would just have to reverse this. But you could actually just take a reciprocal, I think, and get to where you had to be. But it's probably best if you do get a negative just to go back and work it. And unless you're looking at a decrease in temperature, then it should be a smaller value. It should be a value less than 1 right down here. Anyway, so all I've got to do is put in my values. The other thing that catches students with this question is, and it'll also happen with delta G and delta H's and things, you've really got to watch your units here. The units here are kilojoules per mole, but when I put it into this equation, you remember that my R is 8.314 joules per Kelvin per mole, and this is why I like to use the units in my calculations, because I can see straight away if I'm going to do something incorrect. So here I had to convert the 100 kilojoules per mole into 100,000 joules per mole. Okay, so that way I can cross off the units, and the per mole and the mole cancels, and this becomes Kelvin up the top here, and that'll cancel off here. So units are a good way to make sure that the equation you're using is correct, and the values that you're putting into that equation, I should say, appropriate unit-wise. So the comparison of K2 to K1 comes out to be 3.6. So it means K2 is 3.6 times as big as K1. So determining reaction orders and rate law. So this is a very common approach to establishing what a rate law is. So let's have a look at the following data and determine the rate law for A plus B plus C plus goes to D plus E. So here, if you look at, we might have some initial concentration of A 1.2, B's 1.5, C's 0.7, and the rate was 3.26, so mole per litre per second. When we double the rate from we double the concentration of A from 1.2 to 2.4, we have a look at what's happened to the rate. Now the rate here has doubled. As we doubled concentration of A, we have doubled the rate. So I know my rate law is going to be first order in A, because I've doubled A, and that makes it first order in A. Now let's have a look at doubling B. So which part has B doubled? Well, this is a bit of comparison from 1.5 to 3. So when I look at 1.5 to 3, I've got to make sure everything else is the same. I only want to change one thing at a time. And so when I've gone from 1.5 to 3, as far as the concentration of B goes, the C has remained at 0.7 and the A has remained at 2.4. So I compare this rate to this rate, and I see that absolutely nothing has changed. Because nothing has changed, that means that it's zero order in B. So now doubling C, okay, is going to quadruple the rate. Let's have a look at if that indeed happens. So to compare C, we've seen that we've doubled C, 0.7 to 0.4. The only problem is this is not appropriate to look at this one to compare this rate and this rate, because we've doubled C here from 0.7 to 1.4, but B has changed from this row to this row. B has changed from 3 to 1.5. A has also changed from 2.4 to 1.2. So we need to compare this row with the 1.4 in it, because that's where C has changed, to some other row where B is the same and A is the same. So these two values are the same in the first row. 1.2, 1.5 are the same, and so I can compare this rate to this one, because all that's happened from this row to this row is a doubling of C. So I look at the effect in isolation. I've got to look at the effect of doubling C to what it does with the rate, and I can see that this is actually quadrupled. When I go from here to here, there's a multiplying factor of 4. So a doubling in the rate changes the doubling in the concentration changes the rate by a factor of 4. So that would be 2 squared. Okay, so doubling the concentration quadruples the rate, meaning that it must be a power of 2 that has caused that. I hope that makes sense, because remember that our rate is expressed as this K times the concentration of our reactants, and so again with a doubling of the concentration of A doubled the rate. That's first order, because it's a simple 1-to-1 ratio. I don't know if that's the right way to say it, but it's a simple cause and effect. You double the concentration, you double the rate. That must be a power 1 that's caused that. With B, we double the concentration and nothing happened, so it's B to the power of 0. With C, we double the concentration and quadruple the rate. So if you put a 2 in here, for instance, for the concentration of C, 2 squared is 4. Okay, so that's why the rate would quadruple when you double with C. So I hope that makes sense. If, for instance, you double it and you got an 8 times rate increase, then the power would be 3, because 2 to the power of 3 gives you 8. Okay, if it was 16 times, then when you doubled it, you got 16 times, then the power would be 4, because 2 to the power of 4 equals 16. So I hope that makes sense, and perhaps the textbook and some other resources might help you a bit better. So I can rewrite this as K times A. I don't worry about putting the 1 there. I don't worry about including the B, because it's just a B to the power of 0 is just 1 anyway, and so I write it like that neatly. So let's have a look at catalysis. Now catalysis is used in 90% of industrial processes, and basically a catalyst will reduce the activation energy. So if you have a look at a reaction coordinate, which might have just occurred like this, a reaction energy profile, we go from the reactants up this hump, and down to our products, uncatalyze the humps quite large. When we put a catalyst in there, it reduces the size of the hump. So the activation energy 1, I know it's a bit hard to read, but that's EA1, comma 1, is this height from the bottom to the top of the hump, and the activation energy 2 is from the bottom to the top of this hump. And so we can see that activation energy the activation energy 2 is less than the activation energy 1. Okay, so now let's have a look at intermediates and catalysts. So catalysts lower the activation energy and sometimes also facilitate reactions. What I mean by that is some reactions just won't occur without a catalyst, and so it's not just quite as simple as a lowering of the activation energy. It can also be shape selective and things like that, but I won't go into too much detail there. Intermediates are species that occur throughout a reaction. It can be, to the untrained, it can be often hard to distinguish an intermediate from a catalyst, but we're going to do just that now. So these intermediates are species that occur throughout a reaction, but they don't end up in the final products, because as soon as they're formed, they're also going on to the next step. Most chemical, well, I don't know if most, but a lot of chemical reactions occur via different sequences of steps. Different steps occur to give an overall reaction. We often only see the overall reaction, but there might be many steps that are involved along that pathway. Okay, so both catalysts and intermediates are not consumed overall. This is the other aspect of a catalyst, is that it's not consumed. It's not really reactant. It's you'll get back out what you put in with the catalyst. So if you use, theoretically, if you use 5 grams of catalyst in a certain reaction, after that reaction is completed, you should still have your 5 grams of catalyst. Okay, intermediates are the same, you just don't add them at the start. Okay, so that's how we distinguish between them. So a catalyst can be identified by the fact that it appears in the initial reaction step as a reactant. Okay, so it's not technically not a reactant, but it facilitates it, but it will appear on the left-hand side of the initial step. So let's have a look at this reaction here. The question is, identify the catalysts and intermediates in the following reaction. Now this reaction is actually in your ACS textbook, so you might want to have a look at that too. Okay, so we go through here. This is the first step. So we've got our CH3, CH2Br, our AlBr3, AlBr4 minus, CH3, CH2 plus. Okay, so this is the first step of reaction. So then the second step is this. Our third step is this. So overall, what we'd have as our reaction is the CH3, CH2Br plus C6H6 gives HBr plus C6H5 CH2 CH3. How do I know that's going to happen overall? Because I add up all these reactions. So if I add the first one to the second one to the third one, I'll get this bottom one, because a lot of this will cancel. The AlBr3 on the left will cancel with this one on the right, because remember, when I add them all up, I put everything on the right hand side of the arrow, add it all up together, and everything on the left hand side gets added up together too. So when I do that, I'll have terms of AlBr3 on the left, one of those, and an AlBr3 on the right. I'll also have an AlBr4 minus on the right, and that will cancel off with an AlBr4 minus on the left. I will have a CH3 CH2 plus on the right, and I'll have one on the left. And what else do we have there? This larger one, the C6H6 CH2 CH3 plus on the right, will cancel with this one on the left. So all up, I could see that this is going to be the overall reaction. So identifying all those species here, they're not consumed. Really, when I say not consumed, they're really not produced in large quantities either. As soon as this one's produced, say 1 molecule this is produced, it's immediately used again, you see, and so it's not going to be maintained. So I guess consumed is not the right word, but the concentration just doesn't vary. But the only one that appears as a reactant here is the AlBr3. Now again, the catalyst isn't technically a reactant, because see, it's going to come out at the end. You get your catalyst back at the end. Okay, but all these other ones are involved in intermediate steps. So the term intermediate means that they're in the middle. Okay, this catalyst is not in the middle. It's used to facilitate the reaction. But because the AlBr3 appears as a reactant in the first step, and it is the catalyst. intermediates are the other ones. So the other ones are all called intermediates. Not all the species, just the ones that appear and disappear. So I hope that helps. So I have another quick question. A second order reaction has an initial concentration of 2.7 moles per litre. After 20 seconds, the concentration was 1.8 moles per litre. Calculate the rate constant. So for this problem, you're going to use the integrated rate law. So we have 1 over our A equals 1 over A naught plus KT. That's the integrated form of the second order rate law. And we put in our values, and we're just looking for K here. And so I go through this calculation. And so K is going to equal 1 over 20 seconds times 1 over 1.8 mole per litre, take away 1 over 2.7. And I get the 0.093 litres per mole per second. And so that's where we'll leave off for today. Please contact me if you have any trouble understanding some of this stuff. Referring to the textbook and the ACS workbook is going to help immensely, as will any internet resources that might be able to help you along the way. And so never shy away from searching for some other chemistry related websites that might give you some more insight on this as well. Okay, thank you.